Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll continue our discussion on the topic of controllability of network systems. To be precise, we'll try to specify that in general, in any network where we are trying to study controllability, we know that there's an external input. But how does this external input enter the system? Additionally, we are also interested in figuring out what is the underlying protocol which dictates how the states of these agents evolve with time. Why are these two things important? They are important because they also play a role in determining whether or not the system is controllable. So let us see how these parameters play a role, and let's try to understand it better. In the given setup, let us consider a group of agents who form an interconnected system. We saw some examples of this in the previous lecture, like a wireless sensor network or a social network. They consist of agents or individuals. So in the case of the wireless sensor nodes, it is the sensor nodes itself which form the network. And in the case of social networks, individual or people form the network. And together, both of these systems are interconnected. Now, of this group of agents which is forming the interconnected system, we consider one of the agents one or some. To act as the leader of the group. And what is our objective thereafter? Our objective, let's write it. The objective is to derive conditions on the network topology that can ensure that the leader or leaders or let's put it this way, that the group of the agents can be controlled by the leader. So this is how it goes. What we have is a group of agents. Of these agents acts like the leader of the group. Our objective is to derive conditions on the network topology that can ensure that the group can be controlled by the leader. Let me highlight one more thing here. So in today's topic, we will not look at or will not try to answer the question that which agent should serve as the leader. Rather, we say that the leader is chosen arbitrarily out of the given set of agents. Let us discuss a few more properties associated with the agents in the network. So, what are the properties that are associated with the agents? First is there are n number of agents were connected over a digraph or a directed graph. Secondly, the agents have single integrator kinematics. What is single integrator kinematics? It means that the rate of change of, let's write it here, the rate of change of xi, which that means xi dot, is equal to ui, where what is xi? Xi is the state of the ith agent. Furthermore, we make one more assumption, that is, without loss of any generality, we assume that the state associated with an agent is scalar, meaning every xi is a scalar. So what does this mean? This means that, let's go back to the example of a wireless sensor network. In that, suppose each sensor node is focused on measuring only the temperature of the surrounding. In that case, its state is just a scalar which gives us the value of the temperature. But now, let us look at yet another example of a set of interconnected robots. In general, the position of the robot is defined by both its x coordinate and y coordinate, meaning its position, its current state, which is the position, has two parameters, x and y. Then xi need not always be a scalar. However, the results that we describe or discuss in today's lecture can easily be extended even when xi is not a scalar, even to those scenarios. With this setup, we know that we have a set of agents. Among them, one of them is serving as the leader. And these agents follow single integrator kinematics. In this setup, how can the leader drive the rest of the agents in the network? For that, let us talk a little bit about what this UI should be, the control input. For the in the group, Ui is given by this expression. Ui is equal to minus of 1 by the out degree of the ith agent times the summation over j, where j is nothing but the out neighbors of I. And we have xi minus xj. Let's try to understand this control input a bit better. Suppose this first term was not there. Then what does this look like? Please pause the video here and try to guess for yourself. What does this look like? Have we seen this before? The answer is yes, we have seen this before. This entire thing is nothing but the Laplacian flow. When we add this term 1 by d out, all that we are doing is normalizing the Laplacian flow. So now let me highlight one more point. All the results which will be discussed in this topic hold even when xi dot equals ui, which is equal to, so now instead of writing xi dot, let's simply write x, the larger state n cross 1 state vector, that is equal to minus Lx. Meaning, rather than using the normalized Laplacian flow, even if we use just the Laplacian flow, all of the results that we discuss hold the same. So can we write this a bit more concisely, the way we have written here? For the larger n cross 1 state vector, how would we condense this expression for the entire group? We write for the entire group, the overall kinematics is given by, remember that this is a normalized Laplacian flow. Hence, x dot is equal to, one part of it is definitely minus Lx, but it's not just that. It's equal to the out degree matrix, its inverse, times the Laplacian flow. This inverse does the job of normalizing the Laplacian flow. So now we understand a bit more about how the agents are interacting with each other. All of them are being, or their kinematics is being governed by the normalized Laplacian flow. With this, let us now try to understand how does the leader act a bit different as compared to the followers. Because the leader has the task of driving the rest of the agents in the network. So how exactly is the leader able to do that? We now try to answer that. For any group, we partition the set of vertices or the set of nodes associated with the digraph into two parts. One is the set of leaders and the other is the set of followers. So consider a digraph G over which the agents in the network are connected to each other. Within this setup, we now partition the set of vertices. So remember that G is associated with V, comma E. What we say is we define VL as the set of leader nodes, or simply the set of leaders, and VF as the set of followers, such that V is given by VL union VF and VL intersection VF is the null set. Let's look at a quick example of this. Let's consider the digraph shown in this figure. This is an undirected graph. However, we can do the same for a directed graph as well. Now, what we observe is that we have partitioned the network such that the nodes in green now denote the leaders in the network, and the nodes in blue act as the followers. So let us write it. In this network, we say VL consists of 5, 6, and 7, and VF consists of 1, 2, 3, and 4. So how are the leaders able to control the followers? This is because we further say that in this particular framework, the control inputs are applied solely to the leaders in the network. Meaning, let us mark here some input U. So this input affects only the leaders in the network. And this is an external input. So what is happening to the followers now? The followers are influenced by, first is obviously the leaders, and the second is the inter-follower communication. So this is the current setup. The leaders now have some control inputs which are being applied to them, and the followers now get affected by both the leaders and the inter-follower communication. Note that, importantly, the leaders do not get affected by communication with the followers. Rather, the leaders do not communicate with the followers in such a way that they get influenced. Further, so that we can do the computations a bit more easily, let us do a few more arrangements. Suppose now, let the state of the leader be some z. We say that we index the leader as the nth node in the network. So what are we saying now? So without loss of any generality, we have assumed that there's one leader in the group. But of course, it can as well be extended to multiple leaders. And we say that what we do is we stack all of the leaders as the last few nodes in the state vector. Here, this would imply that since there is just one leader, it becomes the last node in the n cross 1 state vector. Further, the state vector of the followers is denoted as some y which takes the following form: x1 to xn minus 1. Then the overall state vector becomes so this now is our n cross 1 state vector. This becomes equal to this. Simply y and z appear together. So this entire process has been done mostly to simplify the computations. To further simplify the analysis, we say that suppose G were an undirected graph, then communication with the leaders or leader is unidirectional. Inter-follow communication remains bidirectional. Just to give an example, let's again consider the same network. So effectively what happens is, suppose this was our original network, then it changes to the following form. All the edges from a leader to a follower. Remember that the nodes in green are the leaders and the nodes in blue are the followers. So all these edges are now unidirectional. And the edges between or the interfollower agents or the interfollower communication remains to be bidirectional, meaning those edges continue to be undirected. With this, let us see how the normalized Laplacian flow behaves in this setup. So we continue discussing the leader-follower dynamics, and now we consider an undirected graph which satisfies the following. Before that, let us take a quick example to see what exactly is a normalized Laplacian flow. Consider the network shown in this figure. For the system, the Laplacian matrix is two is connected to both 1 and 3 is connected only to 1. This is our standard Laplacian. When we apply the Laplacian flow, then we simply use x dot equals minus Lx. Now we are interested in applying the normalized Laplacian flow. In the case of the normalized Laplacian flow, x dot is now equal to minus of first the inverse of the out degree times the Laplacian times x. What is the out degree matrix? Node 1 has a degree of 1, node number 2 has a degree of 2, and node 3 has a degree of 1. Remember that now we are looking at an undirected graph, hence its out degree is same as the in degree. So we simply write it as d inverse Lx. So what is d? 0, 0, 0, 2, 0, and 0, 0, 1. We have to take an inverse of this. In the case of a diagonal matrix, the inverse of a diagonal matrix is done in the following way. What simply happens is every diagonal entry simply becomes the reciprocal of that particular entry. Hence, this is D inverse. D inverse now has to be multiplied with the Laplacian. Times x. So when there is any matrix given to us, and that matrix is getting pre-multiplied with a diagonal matrix, then the entries of the diagonal simply scale the rows of the matrix. Meaning this simply becomes minus half, 1, and minus half, and 0, minus 1, 1 times x. So again, all that has happened is now we see that the rows have been normalized. So this is exactly what a normalized Laplacian flow looks like. In this setup, we are now making node number 3 as the leader node. And that leader node should not be governed by any inter-follower or inter-agent interaction. Rather, it only has to be governed by the external input. So how does the dynamical setup change? Does x dot continue to remain equal to minus d inverse Lx? The answer is no. We now change the setup slightly. Let's see how do we change it. So we write the modified Laplacian based flow. So remember that before this, we had segregated the overall state vector into two parts. Y denoted the state of the followers, and Z denoted the state of the leader. Then what we claim is that you already know that x dot should be equal to minus. So let us assume that from now onwards, the underlying setup is an undirected network. But again, these techniques can be extended easily to directed networks as well. So D out is the same as D. So I'll simply write D inverse L X. Then we can always partition the matrix D inverse L into the following form. D inverse L can be partitioned into 4 parts. Let's call it L prime FF, L prime FL. Since now we are considering a symmetric network, let me simply write here FL again. If this were not a symmetric matrix, we would have simply written LF. Okay, and this is LL. A few more important things to add. What is the dimension of L prime FF? It is n minus 1 cross n minus 1. And this here is a scalar. LFF pertains to only the interfollower communication, which is now governed by the Laplacian flow or the normalized Laplacian flow. What we claim is that in this formulation, now let us apply this partitioning. We say that x dot, which is now equal to y dot and z dot, should take the following form. So what has happened here? We have now modified the original Laplacian flow into something like this. What we have done is, we have now made L, sorry, there should be a prime here. We have set L prime FL. Okay, it's not exactly the same as L prime FL. There should be a transpose here. But we force this part to be now equal to 0 and this as well to be equal to 0, meaning the leader is not influenced by any of the followers. Rather, the leader receives an external input UN. So under this framework, the follows dynamics is given by y dot is equal to minus Fy minus Rz, and z dot is simply equal to Un. So now our purpose has been achieved. The followers continue to evolve under the Laplacian flow with an additional input which comes from the leader in this manner. And the leader does not get affected by the followers at all. Rather, it gets affected only by the external input Un. So now, this is a framework which looks very much like the standard x dot equals ax plus bu. And we know how do we study the controllability of this system. So we can now straightforwardly apply the controllability formulations and check whether or not the leader can actually control the rest of the followers in the network. So again, for the example that we had before, let us construct the matrices F, R. So R in our case is a scalar because we've considered a single leader. But let us go back to that example given here. So for the same example, we are interested now only in the normalized Laplacian flow. Further, this normalized Laplacian flow affects only the followers in the network. So let me erase this. And now we know that the third node, so let's modify this. This becomes bidirectional. And we partition the network in this manner. So this submatrix given here is our matrix F. Sorry, R is not a scalar. My bad. This part is a scalar. And R is a column vector because it is akin to B in BU, AX plus BU. So this here is our R. This is F. And the modified flow expression becomes X dot, which is now equal to some Y dot and Z dot is equal to F, which is this R, and minus should come here, minus 0 and 0. But not only this, we also have an external input, which is now affecting. So we can write it as U3. So the dynamics becomes Y dot is equal to, again, minus Fy plus Rz, and Z dot is equal to Un or U3. So Z is the state of the leader, which acts as an input. Sorry, this should be minus. Z is an input. It is the state of the leader, and that acts as an input which for the set of followers in the network. And this is what the modified flow looks like, where F is given by this and R is given by this. So please take a note of it. R here is not a scalar, but rather a row vector. LL is always a scalar. Sorry, R is a column vector. We end today's lecture here. In the next lecture, we will see how, when we apply the controllability conditions, how does the topology come into picture? Or how does the topology help us in figuring out the controllable configurations? Thank you.